Welcome to EDU World Space.
We're given the circuit diagram on the left. In the book, they, instead of labeling these E1, R1, R2, R3, E2, and R4, they put the actual numbers on the circuit, but I labeled them this way because it's a little bit easier to work with. And the values are given above, where the EMF for battery 1 is 16 volts. The internal resistance associated with that battery is 1.6 ohms. The resistor R2 has a value of 5 ohms. The internal resistance of the battery below R3 has 1.4 ohms, and the associated EMF is 8 volts. And the final resistor has a value of 9 ohms. In part A of this question, we're asked to find the current in the circuit, both its magnitude and its direction. So there are two batteries here, which means that the current could be flowing in one of two ways. It can either be flowing in the clockwise or the counterclockwise direction. So that is, if it's flowing in a counterclockwise, it'll be flowing from B to A to C, which I forgot to label here. So it's just going around this way if it's counterclockwise. And if it's clockwise, it's the other way around, A to B to C. So I'm going to make a guess, and I'm going to assume that the current is flowing counterclockwise. And it actually doesn't matter which direction I pick, because the sign of the current will tell me whether or not I pick the right direction or if it's the opposite direction. And what I mean is, when I solve for the current, say I assume that it's going counterclockwise, if I get a positive value for the current when I solve for it, then that means this direction that I've picked is the correct one. And if I get a negative value, then that means the direction that I picked, the current is actually flowing in the opposite direction. So if I turns out to be negative, then it'll be flowing clockwise instead of counterclockwise. So the way to solve for I is to remember that if you start at a certain point in the circuit and you come back and you make a full round trip so that you end where you started, then the total potential difference, the sum of all the potential differences that you encounter, is zero. So let's go across. We start here at the first battery, and then we're just going to make our way around in a counterclockwise direction. So we encounter EMF 1, and then there's R1 with the current I, so there's that voltage drop there. And then another voltage drop of R2I, right, and as we go across here. And then the next resistor we see is R3. So the voltage drop is R3I. And now we're going across, we're crossing this other battery here. But this is the positive side and the negative side. And the way that we determine the sign is when we go from negative to positive, that's a plus sign. When we go from the higher potential end to lower potential end, and over here we're going in the opposite way. We're going from the lower potential to higher potential in terms of the battery. So we're crossing the battery in the opposite way. So we have to put a minus sign to account for that. And then we have a voltage drop here, minus R4I. And that's equal to zero. So that's the total, the sum of all the voltages or the potential differences in the circuit. So we want to solve for I. So let's actually collect all the terms with I and rewrite this equation. So minus I, and this here will just be the sum of all the resistance that's in the circuit. And we can easily solve this equation for I. So it's just the difference in the EMF over the sum of the resistance. And we actually have all the numbers. So that's 16 volts minus 8 volts over R1, which is 1.6 ohms, and R2, which is 5 ohms, and R3, 1.4 ohms, and finally R4, which is 9 ohms. So we find that the current is 0.47 amperes. Now we'll move on to part B. Okay, so part B, we're asked to so find the terminal voltage VAB of the 16 volt battery. So let me quickly just give a sketch again of the circuit. So we can have our points of reference. So remember, this is B, this is A, this is E1, this is R1, and yeah, that's all I need for this particular part of the problem. So I'm not going to label in the rest, but what we're going to do is we'll start at VB and we're going to go over here to VA. So I'm at VB, and then I pick up a contribution from the battery, and then I have a voltage drop here of R1I, and that should be equal to VA. And then VAB is the difference between VA and VB. But VA is given by all of this stuff over here. So VAB is equal to VB plus E1 minus R1I. And then VB. So all of this is VA. So VAB is equal to E1 minus R1I. And again, we have the numbers for all of this stuff. So that's 16 volts minus 1.6 ohms times 0.47 amperes, which is the current we found in part A. So VAB is 15.25 volts. Right, so A is at a lower potential than B. Okay, and now we move on to part C. So part C, using the potential, so we have to find the potential difference VAC of point A with respect to point C. So it's similar to part B, except that we're finding the potential difference between A and C rather than A and B. So again, let's draw the circuit so we know where everything is located. Okay, so that's R1, and this is E1, and that's R2, and that's R3, and this is E2, that's R4. This point is A, and this point is C. And actually, you can find that in one of two ways. So you can go from A to C by traveling this way, or by traveling this way. Either way, it should give you the potential difference. So um, let's pick. Uh, let's go with the black line. Okay, so we start at VC, um, and then we pick up a contribution from that EMF, and normally when we go across this resistor, it would be a minus IR3, but we already know that point A is at a higher potential than point C. So when we go across the resistor, we actually put a plus sign, like so. And the same thing here when we go across R2, and that's equal to VA. So VAC is VA minus VC, which is that EMF plus I R2 plus R3. And that gives us here 8 volts plus 0.47 amperes. And R2 is 5 ohms, and R3 is 1.4 ohms, and that gives us 11 volts, right? And you can repeat the procedure by going the way of the blue line, and it should give you the same result. Okay, and now we come to part D of the problem. And in part D, they're asking you to use figure 25.30 as a model to graph the potential rise and drops in this circuit. So we're going to model after that figure that they reference. So just the figure that they reference here is 25.20. Okay, so we use that as a model. So over here, we have 16 volts, and we'll start at point B, so we put that there, and point A is a little bit a ways from that, and then point C is a little farther away. So let's see if I can do this justice. So we're here, and then we move a little bit, and then we see that potential difference, the drop in potential because of the internal resistance, and then we move along until we encounter another resistor, that R2 resistor, and then we move along in a constant way until we encounter R3, and then we're constant for a little bit, and then let's see, and then we have like a big drop, and then we're constant, and then another big drop. So this big drop is from the 8-volt resistor. This drop is from the R4. That's from R3. That's from R2. And that's from R1.